Problem 3.74. In this problem, oil of a specific gravity 0.83 flows in the pipe shown in the figure below. If the viscous effects are neglected, what is the flow rate in this pipe? Okay, so the first thing that we're going to do is we're going to label the points of interest. We're going to label this to be 0.1 and this to be 0.2. Okay, and then we're going to do some other labeling. This is supposed to be 3 inches, so we're going to call this diameter to be D, lowercase, and this one to be uppercase. We're also going to look at the points that we have in the manometer. This is 0.3. We're going to label this 0.4. And the only thing we're missing is the elevation, so I'm going to write from here to be H. Okay. Now that we have all the labels, what we need to do is create a table of the information given for each one of the points in the pipe. So we got for 0.1 and 4.2. We're going to write pressure, velocity, elevation, and areas. Okay, so the pressure in both points are unknown at this moment, so we're going to do question marks. Velocity at 0.1, notice that it has a tube that measures the static pressure. Therefore, the velocity is 0 because it's an stagnation point. So velocity is 0. Then we have a 0.2, have a static pressure. The velocity is unknown. The value of the elevations is unknown. However, the only thing that we know is that they are the same for both of the points. So that's exactly what we're going to write. That is the same. And the areas are going to be pi d squared over 4 and pi capital D squared over 4. Okay, so now that we have all the information, we're going to write the Bernoulli equations between 0.1 and 0.2. So we have P1 plus 1/2 rho, and this is of the oil, V1 squared plus gamma of the oil, Z1, is equal to P2 plus 1/2 rho of the oil, V2 squared, plus gamma of the oil, Z2. We're going to cancel out the information based on what we have on the table. Velocity at 0.1 is equal to 0, so this cancels out. And the elevations are the same, so this cancels with this. Then at the end, what you have is that P1 is equal to P2 plus 1/2 rho of the oil, V2 squared. The next step is to write a relationship between the pressures between 1 and 2 using hydrostatic pressure. So we're going to start. I'm going to do P1 is equal to P2. Then we go from this point to 0.4. We go up, so it's negative, and it's gamma of oil times the elevation between 0.2 and 0.4, which is H, plus this height, 4 inches. I'm going to call it H1 for this moment. So H plus H1. Then we go from 0.4 to 0.3. We go down, and it's water in that case, so water times H1. And then we go from 0.3 to 0.1. We go down, so it's positive. We go gamma of oil times the elevation between those 2 points, and we'll label it as H. Can I multiply this out? So things cancel out. P1 is equal to P2 minus gamma of oil, H, minus gamma of oil, H1, plus gamma of water, H1, plus gamma of water, H. And notice that these two cancel out. And that has to be the case. You only are left with the dimension inside of the manometer. Okay? So notice we are going to rewrite these two equations. So we're going to write P1 minus P2 is equal 1/2 rho of the oil, V2 squared. And we rewrite this one as P1 minus P2 is equal to gamma of water, H1, minus gamma of oil, H1. And this is the same thing as gamma of water, H1, minus Sg, gamma of water, H1. And we factor things out. We have gamma of water, H1, and this is 1 minus Sg. So these are the two equations that we have at the moment. Physically, the information that we know is that the relationship of the pressure obtained in Bernoulli's has to be exactly the same to obtain with hydrostatic pressure calculations. So we could make them equal to each other. So we have 1/2 rho of oil V2 squared has to be equal to gamma of water H1, 1 minus Sg. Okay, now let's substitute a couple of the values. So we have 1/2 Sg rho of water V2 squared is equal to rho of water times G H1, 1 minus Sg. And notice that we cancel the density of water on both sides. And we solve for velocity at point 2. Velocity at point 2 simply becomes the square root of 2g H1, 1 minus Sg, divided by Sg. We substitute all the values and make sure that you have the proper units, and you should get 2.10 feet per second. Now our goal is to find the volume flow rate. So Q is simply, we evaluated at point 2 because that's where we have velocity, A2 V2. So it's pi. The diameter is 4 inches divided by 12, so we make it into feet, square divided by 4. So this is in feet. And then we multiply it by 2.10 feet per second. And then we are left with a value of 0.183 feet cubed per second. And this part, the key part, is to make sure that you transform from inches to feet so that units work out.